So in this video we're going to do a worked example of a variation of parameters problem. And there's a lot of nice algebra, so we're hoping that we don't make too many errors. So step number one is to make sure that your second order linear differential equation has a coefficient of 1 on the y double prime term. It does. If it didn't, we would divide through by whatever coefficient was on the y double prime term. But because there's a 1 there to begin with, we can go directly into the solution process. And step number one is to find the complementary solution to the homogeneous differential equation. So to do that, we would find the characteristic polynomial, which would be r squared plus 3 times r plus 2 equals 0. And then we solve the characteristic polynomial for its roots. So if we do that, we get this times this equals 0. And we're going to be able to factor this as r plus 2 times r plus 1, which tells us our roots are -1 and -2. So the complementary solution, the solution to the homogeneous differential equation, is going to be y complementary equals c sub 1 e to the negative x plus c sub 2 e to the negative 2x. And then we know that solutions are going to have the form y complementary plus y particular. So we guess that y particular is going to equal a function u sub 1 times the first solution, which was e to the opposite of x, so e to the negative x, plus some function of x, u sub 2, times y sub 2, but y sub 2 in this case is e to the negative 2x. So again, we needed, from the previous video, we need a y sub 1 and a y sub 2 that are linearly independent solutions to the homogeneous differential equation. And then we guess that the particular solution is going to be a function combination of those two homogeneous solutions. So once we've done this step, we then calculate the Wronskian of the solutions y sub 1 and y sub 2. So the Wronskian of those two solutions is going to be put the solution in and the derivative of the solution, put the second solution in and the derivative of the second solution. So we calculate the Wronskian. So we get the product of the main diagonal. So we get -2 times e to the negative 2x times e to the x is -3x minus the product of the other diagonal. So we're going to get minus a negative is a plus e. And e to the negative 2x times e to the negative x is e to the negative 3x, which simplifies to just negative e to the negative 3x. So there's our Wronskian. And then using Kramer's rule, we replace the first column of this with 0 and our function f of x. So 0 and sine of e to the x. And then we keep the second column of w. So we get e to the negative 2x, negative 2 e to the negative 2x. And we calculate this determinant, so we get 0 minus the product of the other diagonal, which is e to the minus 2x times sine of e to the x. And then we need to calculate w sub 2. And for w sub 2, we keep the first column of the Wronskian. We keep e to the negative x, negative e to the negative x. And then we replace the second column with 0 and our function f of x, like we saw in the previous video when we developed the theory for this solution method. So this equals the product of the main diagonal minus the product of the other diagonal, which will 0 out. So we just get e to the negative x times sine of e to the x. And then the solution method is that we use Kramer's rule to show that the function u sub 1 prime, so we're trying to find u sub 1 and u sub 2, but we know from the previous video that u sub 1 prime is going to equal the ratio of w sub 1 and w. So that ratio is going to be, w sub 1 is going to be negative e to the negative 2x times the sine of e to the x, and this is going to be over w, but w is the opposite of e to the negative 3x, so the opposite of e to the negative 3x, and that simplifies to e to the x sine of e to the x. And that means to find u sub 1, we have to take the antiderivative of u sub 1 prime. So u sub 1 is going to equal the antiderivative of u sub 1 prime, but u sub 1 prime is just e to the x sine of e to the x, and we're integrating with respect to the variable x, so dx. And if we integrate this, we're going to get, it looks like we get negative cosine of e to the x. And we could verify this through differentiation. The opposite of the derivative of the cosine of e to the x, so the opposite of negative sine of e to the x is going to be sine of e to the x. And then the chain rule says take the derivative of the inside is e to the x, so the derivative of this gets e to the x times the sine of e to the x, and the work checks. So here's u sub 1. I'll put a little box around him so that our attention is drawn to him in a little bit, because we'll need him to substitute back in up here for y particular. So then the second thing we saw in the previous video was that u sub 2 prime, the derivative of the function, second function we're looking for, is just the ratio of w sub 2 over w. And w sub 2 is e to the opposite of x times the sine of e to the x divided by w, which is the opposite of e to the negative 3x. And this simplifies to the opposite of e to the 2x times the sine of e to the x. So u sub 2 is going to be the antiderivative of u sub 2 prime, so u sub 2, we'll do the work up here, I think. We're going to need some space on this one. This is a more complicated integral. So u sub 2 is going to equal the antiderivative of this stuff, so the minus can factor out front, and we'll get e to the 2x times the sine of e to the x dx. And then this isn't going to integrate so easily, so what I want to recognize is that e to the 2x is the same as e to the x times e to the x. And so here I can make a u substitution. I've used u sub 1 and u sub 2, so it should be okay to use just plain u. So if I make the substitution, u equals e to the x, then du dx is going to equal e to the x, which means du equals e to the x dx. So u sub 2 can be written as the opposite of e to the x dx can be replaced with the du, and the other two e to the x's can be replaced with the substitution u equals e to the x. So I wind up with the integral u times sine u du, replacing this e to the x with a u, e to the x dx with a du, and e to the x here with a u to get the sine of u. And this looks like it can be solved using integration by parts, or I could probably look this up in the integral tables that we have. So we got the comprehensive table of integrals that was given to you way back in Calc 1. So you could use the table of integrals or an integration by parts. So I've used u sub 1, and u sub 2. So I'll do an integration by parts. I'll let u sub 3 equal u. And the reason for doing that then is u sub 3 prime is just going to equal 1. which means I need to let v prime equal sine of u. And then the antiderivative of v prime would be minus the cosine of u. So u sub 2 could then be written as, using this, the opposite of, we get u sub 3 times v, or u times the opposite of the cosine of u. We get u times the opposite of the cosine of u, minus the antiderivative of the product here, u sub 3 prime times v, but 1 times negative cosine u is negative cosine u, so this negative here is going to let me write this as an addition, and we're integrating cosine u du. So when we do that, we're going to get a distribution here. I'm going to get u times the cosine of u minus a sine of u. And the substitution we made was u equals e to the x. So ultimately then u sub 2 is going to equal e to the x cosine of e to the x minus the sine of e to the x. And then now we have u sub 2, we still have to put everything together to find y particular. So y particular, we said, is going to equal u sub 1 times e to the negative x, but u sub 1 is minus the cosine of e to the x, and then we need to multiply that by e to the negative x, and then it's going to be plus u sub 2, which is this mess right here, e to the x cosine e to the x minus sine e to the x, and then this needs to be multiplied by e to the negative 2x, so e to the negative 2x. And what we're going to see is this cleans up a bit. So right here I have a minus e to the minus x times the cosine of e to the x, and then I distribute this in, I get e to the minus 2x times e to the x is going to be plus e to the negative x cosine e to the x minus e to the minus 2x times the sine of e to the x, and then these two cancel out, and I wind up with just y particular equaling, just the opposite of e to the opposite of 2x times the sine of e to the x. And so then you have to put it all together. So we're still not done because we're trying to solve the differential equation. So I'm going to get rid of my characteristic polynomial up here, and we really need y complementary plus y particular to give us our general solution for the differential equation. So our solution is going to be y complementary, which is c sub 1 e to the opposite of x plus c sub 2 e to the opposite of 2x plus y particular, which we simplified right here. So a plus, a negative is going to be a minus, so we get minus e to the minus 2x times the sine of e to the x. And so what you can see is that this process does indeed give us a solution. It is a tedious process. There are a lot of steps and a lot of places where a person can make pretty simple arithmetic or transcription errors. So it's the type of problem where you don't want to rush and do it. You don't want to try to do it quickly, because the faster you try to go, the more likely you are to introduce simple, silly errors, and then you wind up having to try to find where you made the mistake or do the problem again from scratch. So these are ones where you don't want to procrastinate. You want to give yourself plenty of time so you're not rushed when you're trying to solve the problems.